Everybody. This lecture, that's the 7th in this course 1, and that will be on porosity development, on moisture fixation, and the first lecture is on mechanisms, and the next lecture, lecture 8, is on characterization. Together with the lectures in the afternoon, we expect that in 3 years' time, 4 years' time, when you've finished your projects, they will have to be revised. Okay. So, why are we dealing with this? Well, porosity, moisture fixation, and the state of water in porous building materials, and it's not only concrete, it's wood, masonry, gypsum, plaster, and so forth. They affect the engineering properties. And now we're talking much about materials, but I think you should keep in mind that actually it's the performance of the structure we are interested in. So when we look at the lower triangle here, let's see if I can get the mouse. Yep, we have the constituent materials, cement, sand, stone, water, and so forth. We mix it in a certain composition. The way we mix it has an impact on the potential materials properties. That's the potential properties which the concrete in the truck has. Now it arrives, and we start to cast it. There's a structural design, the cover, that's the distance between the surface and the reinforcement, the configuration of the reinforcement, it could be other types of structural design issues, which has an impact on how the concrete actually ends up in the structure. So the execution, that's the casting and the curing. Concrete is like babies. We need to care about them during the time when they grow up, and depending on how we care about it, it will develop differently. And then what we are interested in as owners, users, that's the structural performance. I haven't made a third triangle, which I sometimes do, and that's dealing with maintenance. Maintenance, repair, the environmental load, or the load, mechanical and environmental load, which has an impact on the service, the performance of the structure during the service life. Okay. So, what do we use this information on porosity and moisture fixation? Yes, we need it for design of new structures. This is the Faro bridges in Denmark, and that was the first time that fly ash was used for a structure. It was also the first time when they used curing technology. That means that they were controlling the temperature of the concrete to limit the cracking and to limit too high temperatures. You saw in the first lecture, or the lectures on Monday, that the temperature has an impact on the porosity. So there's a certain maximum temperature the concrete must undertake in the structure. 50% of the money we use for concrete structures, depends roughly on how you calculate it, but 50% is used for maintenance. Partly because we have problems designing the concrete structures and executing them in a proper manner. Partly because we are not able to do the maintenance repair in the best manner. Increasingly, we have much more understanding of the mechanisms and can do better repair. But a lot of money is going into repair, and we also need to understand how to repair the concrete in a proper manner. That goes both for the assessment, the inspection of the structure, what's actually the problem, and it goes for selecting the right repair methods. Could be that you actually, for this edge beam, that's the side of the bridge, which has had a lot of contact with chlorides and de-icing salts, from de-icing salts. It could be that you chose actually to use a surface treatment. But if you do that, and you may have ingress of water, you may end up with freeze-thaw problems. And that has actually been experienced. Well, you helped with the corrosion, reinforcement corrosion, but you got another problem. So that's why you need to understand which technique to use where. Okay. And I think that during the afternoon we'll have more information on the impact of moisture on various deterioration mechanisms. So what to bring home? First of all, pores are an inherent part of the cement-based materials. We have them, we have to deal with them. Pores in cement paste, they range from nanometers to micrometers, and if you're talking about concrete, which we normally are, it will be to centimeter range. The definitions of pores vary. That means that when you go into the literature, you will find the same word meaning different things. And you will find different words meaning this, having the same meaning. And also when you use predictions, you need to know what are they based on. And the volume fractions of, well, the solids and the capillary and the gel porosity can be estimated here. I've made it in, I don't know what it's called. But the capillary and the gel, it's termed differently depending on which model you're using. And then the amount, the size and distribution of the pores, that affect the engineering properties. So that's why we're interested in this. I have divided the lecture into two major parts. One on moisture fixation, sorption isotherms and CSH. You already heard something on Monday. And then the second part on porosity development. Some models we can use to predict it. Some of the features which are not captured with these models, and then a few examples. If you have questions, you're welcome to interrupt. So let's start. This is a sorption isotherm. Often you will not see it fully like this. If we have, it's not that easy. Yeah. So we have the amount of water as a function of the relative humidity. That's a fingerprint of the porosity you're looking at. You can use it for wood, for masonry, for all sorts of materials, and you get a fingerprint of your material. Often you will see that it's only the so-called evaporable water, and often it's drying to 0 or heating up to 105 degrees. But it may differ depending on which methods they're using. So when you're comparing sorption isotherm, you also need to consider that. And then we have the so-called non-evaporable water, which is the water kept in the hydrates, or being part of the hydrates. 105 degrees, that's arbitrary. And you learned on Monday that some of the hydrates actually start to decompose at lower temperatures. So we need to keep that in mind. If we start from a dry material and add an increasing amount of vapor, water vapor, we will see absorption on the surfaces as indicated here. And initially there will be one layer and then additional layers. At around 50% relative humidity, 45–50% relative humidity, we start to have capillary compensation. And then you will see an increase in the water content. The capillary compensation can be described by Kelvin's equation. And here we have the relationship between the so-called Kelvin radius, that's the radius of the meniscus, and then the relative humidity. And here you can see some values where we have the Kelvin radius. This is without the radius of the menisci, is the radius of the pore without the adsorbed layer. So you have to add that. That doesn't have an impact if it's a large pore, but if it's a small pore, it has an impact. And the last number, where we have relative humidity 0.4, that's not reasonable because we don't have capillary compensation at that place. The numbers here, we have the molecular weight, the density, the gas constant, temperature, and the relative humidity. And you will see that sometimes we change the surface tension of the pore liquid by purpose, and we get a different water content, and we also have different stresses being set up in the pore structure, because when we start to have the meniscus, stresses are set up, and we can change these stresses by changing the surface tension. This is shrinkage-inducing admixtures, and I'll not talk more about that today. So again, if we look at the surface, initially, starting from a dry material, we have this a layer being built up on a free surface. And at a certain time, the small pores will be filled. That's here called micropore filling. Whoops. And then later, we will have the capillary compensation. And here you can see this is actually the adsorbed layer, which is small in this drawing compared to the size of the pore where we have the capillary compensation. And if we look at sorption isotherms, this would be the first part where we have the free surface adsorption, and then we have the filling of the micropores. Here we have an example of only capillary compensation, and here we have the combination, and that looks like the sorption isotherms we see for cement-based materials. So the latter part here, the micropore filling, where we have a decrease in the slope, and the next, capillary compensation, and micropore filling and capillary compensation. And here you see it again. And here, that's an intermediate range where we only have the free surface adsorption. From that, we can determine the pore size distribution, making some assumptions of the pore shape. And often you will see that the cylindrical pore shape is assumed. Okay, so this is a graph which you often will see. Here you can see that the gel isotherm is constant above 45% relative humidity, which is not the full truth. I'll show you some slides afterwards. So at the upper relative humidities, we have first the free water, which is up here, capillary compensated water, and then the surface adsorption. And the chemically bound water would be down here. Due to ions in the pore solution, we will not have 100% relative humidity. We will have, depending on the concentration, 98 or something like that. This is a graph showing also sorption isotherms for different water-cement ratio, and the lower is illustrating the cement gel isotherm. And then you have the more in water you have initially, the more water or more capillary pores you will have, and larger porosity in the shown here in the upper range of the relative humidity. And here we have some data from Lars Olof Nielsen, and these are for different concretes. And again, you can see that we have the cement gel down here, and we also have for this cement an equation of how we can estimate it depending on the degree of hydration. And then we have information on how to estimate the amount of water depending on the initial water-cement ratio and the degree of hydration. This is a comparison of, it's also sorption isotherms. It's a comparison of predicted and measured, moisture content at different relative humidities as a function of hydration and as a function. So here you can see, and that's a measurement undertaken by Christina Mjornell, which was a PhD student of Lars Olof's. Initially, we have a lot of free water. We don't low degree of hydration. And as the hydration takes place and we have more and more small pores, we will see that the sorption isotherm move up, and we have many more smaller pores. And also what you see here is that we have, it's not that easy, we have a decrease in the total water content. because we don't have water from the exterior coming in and filling up the pores. We had this chemical shrinkage. This is for one cement, water cement ratio 0.4. If we add silica fume, we get a slightly different sorption isotherm. We see again the trend that initially we have much free water, and then the gel part is increasing as a function of the relative humidity. I should say that I have added some slides, and when we upload the presentations, you will get copies of these. If you compare here, you can see that it seems that we have more gel when we have the silica fume. And can you explain why? Pardon me? Yeah, we have the pozzolanic reaction. Yeah. So we have more CSH. Okay. Then I have shown you sorption isotherms. Now depending on how we measure, if we dry out the sample or if we wet the sample, have water vapor, increasing amount of relative humidities, we'll get different sorption isotherms, as you see here. And when we dry out the sample, you can see it illustrated by this figure, that we have the drying out from these pore sizes. And we may have a larger pore in here, and that's what is giving this difference. On the other hand, if we are increasing the relative humidity, we will have a different mechanism. And the adsorption, you will see that at the same relative humidity, we will have less water in the pores. So that's giving this difference, what we call hysteresis. And I know that several of you will work with this to actually predict it, describe it. It can be rather large. It can be up to 30% the difference, depending on where on the sorption isotherm you are. So it has a huge impact on the performance of the material. If you don't dry it fully out and fully wet it, you will have so-called scanning curves, which are the curves you will see here, back and forth, depending on how the moisture is. The sample is dried out, wetted, dried out, wetted. There's another thing which has an impact on the sorption isotherm, and that's the temperature. The higher the temperature, the more loosely bound the water. So for the same material, if you increase the temperature, it could be in the structure, you will see that there is a change in the sorption isotherm, the higher the temperature. Okay. So the moisture fixation in the CSH, you saw some slides on Monday, and I'll just go through some of this. We have the... Do you have a question? No. Do you have a question?
I'm just wondering, like you said, for temperature we have changes, but you don't say why. So, why?
The water is more loosely bound when you have a higher temperature. Yep. And it happens quite rapidly. We're doing some tests where we're using time domain refractometry to measure the moisture content, and we can see that this actually happens quite fast. Yeah. Okay, the CSH gel. We don't fully understand how it looks yet. There are some proposals, and it seems that this model proposed by Feldman and Serreta in the 70s is quite good. Here it's described as we have the CSH, and then we have interlayer water and adsorbed water. You could say that it actually should be the sheets of calcium and silicium, and then we have the interlayer water and adsorbed water. They describe the porosity with the interlayer space in the nanometer size, and then external pores. When you look into other places, this is from a book on material science of cement and concrete from Meta and Monteiro. And they describe the water. We have the capillary water, which is the free water in the large pores. We have the water held by capillary tension. And then we have the adsorbed water, similar to before. And we have the interlayer water in here. And then what we don't show here, we have the chemically combined water in the other hydrates. And this is a recent figure of a model proposed by Peter McDonald and co-authors based on NMR data. And here you can see, again, the sheets of the calcium and silicium. You have the intra-pore with water, and then you have the inter-sheet pore, which are slightly larger. Now I've talked about the pores in the cement paste, but we should not forget that we also have other types of pores. We have the larger pores up here. We have, by purpose, we entrain air in concrete which has to withstand silica freeze thaw. And these will be pores in the sub-millimeter range, 0.3 we go up to. And then we have compaction pores. And compaction pores, they are pores which where you have air being encapsulated during the casting. These type of pores we want to decrease because they are of no use, and they just decrease, they make the concrete inhomogeneous, and they decrease the strength. But a certain amount of these pores we also will have, depending on the compactability of the concrete, and also depending on the force we actually use to compact it. This is an illustration of the variation in nomenclature used. Just to keep in mind that the size of a gel pore is not the same in all literature. Okay, any questions? So we move into porosity development. When we mix cement and water, we start to have a reaction. Here we have a schematic drawing. We have the cement grains, and we start to have reaction. This is a calcium calcium hydroxide, and then we start to see other reaction products around here. And this dotted is the water. The reaction will proceed, and at a certain time, the hydrates reach each other, and we have this stiffening, what we call the setting. The setting time is arbitrary selected. It's just standardized. We have the initial setting, and we have the final setting. The information is used for how long you can actually work on your concrete and when you can start to do the finishing. So for planning of castings, it's important information. And then we have the increase in solids, and we have what we call the hardening period. You can also see the change here where we start to have dispersed cement particles in water. That's from a workshop at NIST in Gaithersburg, and increased hydration, and here. And when the hydration takes place, you can see that you have more and more solid and less of the pore volume. And you have an increase in strength and a decrease in permeability. And this is normally what we want. Sometimes we want a low strength concrete, then we would like to be able to make that too. Or we want a very permeable concrete. For instance, they are now talking about permeable concrete for drainage of roads. So you don't have too much, you don't use the sewage system too much for that. There has been proposed some models on how to predict the volume of the porosity, or the fraction of the porosity. And there's a simple model which was proposed by Powers and his co-workers. He worked closely together with, among others, Browniot. It's a 70-year-old model, no, 60-year-old model, but it has been used quite a lot, and I think you should know it. It was a benchmark because it allowed quantification of the hydration process. So it was, the assumption is that the water is held in the paste as capillary, chemically bound water. That's the water in the hydrates. It's non-evaporable. That's how it was measured. Non-evaporable below 105 degrees. And then we have the physically adsorbed water, which he called the gel water, and the free water, or the capillary water here. And the evaporable water, meaning the water which was lost until 105 degrees Celsius, that was the gel water and the capillary water. And here you see that the work was based on a huge amount of experimental work. The model is based on a huge amount of experimental work. Sorption isotherms, or water vapor, determination of the amount of non-evaporable water. Here it's shown as a thermogravimetric analysis, but you could also do it by just heating your sample up from 105 and 2000 degrees Celsius. And based on this experimental work, he obtained constants on the amount of non-evaporable water in cement, and here it's 0.23 grams per gram reacted cement. And you will see this figure in much of the literature that is actually used. The gel water, 0.19 gram per gram reacted cement, and chemical shrinkage, which is approximately 6 milliliter per 100 grams of cement. It's quite a lot, actually. So, how much water would I need to have full hydration? 0.42, yeah. If I didn't have extra water coming from the exterior. And chemical shrinkage, you saw it. Here you have put the samples upside down, but you can see that you can actually measure it where you have the paste and then a capillary tube, and you follow just the decrease in the meniscus of the water level. And you can do it continuously. And that's the chemical shrinkage is due to the difference in volume between the reactants and the products. So based on this, he came up with these equations for the volume fractions of the chemical shrinkage, the capillary water, the gel water, the cement gel, which is all the solids, the solid reaction products, and then the unhydrated cement. And here you can see a schematic drawing on the volume fractions as a function of the degree of hydration, where you start out with having cement and capillary water, and then you will have the reaction giving gel solids and gel water, and decreasing the amount of, well, the reaction products, the cement and the water. And in addition, some of the capillary pores are becoming empty due to chemical shrinkage. They can be refilled if we have an open system. If we have small samples, keep them saturated, these pores can be refilled. If we have a huge sample, the water can't penetrate, or if we don't keep it saturated, we have no water. Power's model was based on empirical constants, and we have this unhindered hydration up to water-cement ratios larger than 0.42. If we look at these two examples, we can see that if we have a water-cement ratio of 0.6 and a sealed system, we end up at full hydration with some capillary water left and some empty capillary pores. If, on the other hand, well, first we can see that it's possible to use all the cement. It may take some time if the cement grades are large or if we have a lot of B-light, but it's possible. If we have water-cement ratio 0.3, At a certain time, we have no more water. And if we assume that the gel water cannot be used for hydration, we will have no further hydration. So we don't use all the cement. If we can refill the porosity created, the empty capillary pores created due to chemical shrinkage, we can actually have the hydration to proceed a little longer, and we can have a structure without, microstructure without capillary pores. And what we see, that assuming that we cannot use the gel water, we cannot have full hydration of the cement. So when you're preparing your samples for experimental investigations, you should consider this. Both whether or not you keep them saturated or sealed, and which water-cement ratios you're using. Then you also need to consider that these data, the calculations, they're based on empirical constants, based on cement which was produced in the US 60 years ago. And the cement has changed. We have much more alite in the cement than we had at that time. Here you see an example of if we start to use silica fume, the constants, I don't know if you recognize, but the change in non-evaporable water, that's 0. The gel water is 0.5. Compared to the other, it's much. And the chemical shrinkage is much larger. This is part of the reason that we may have problems with what we call self-desiccation, drying out, self-inflicted drying out of the concrete when we use silica fume. So more water is needed from the exterior. This model, the Powers model, could be improved if we knew more about the cement reacting. If we have information on the reactions taking place, the degree of hydration, and the molecular volume, we know the volume of the hydrates, and we know the composition of the material, we can actually estimate the volume fractions, the chemical shrinkage, the non-evaporable water. So for your material, if you have this information, you can do it better than just using Powers model. And if you know the water-cement ratio, you can also determine the capillary porosity at any degree of hydration. One thing you should also consider that when we are talking about Powers model, we assume that all the cement is reacting at the same rate. It's not that we assume that some of the clinkers are reacting before the others. We have the same relationship between cement used and volume fraction of hydrates developed at all time, at all degree of hydration. We can use a mass balance to determine the amount of reactants. This was shown by Karen on Monday, and here you see that we need to know which reaction products are developed. We need to know the composition of the reaction products, and then we can determine the amount of reaction products assuming a given degree of hydration. We can also do it even better if we use thermodynamic modeling. Here we have the input, that would be the composition of the material and the degree of reaction of the various components. We have information on which phases will develop based on the thermodynamic modeling. And as the output, we have the hydrates, the portlandite, the calcium, the CSH, the ettringite, the AFM phases, and so forth. And in addition, we have information on the solution composition. This becomes extremely interesting if we're talking about chlorides. Chlorides, I think you heard yesterday that one of the problems that we have with deterioration of concrete, actually the major problem, that's chloride-induced corrosion. Chlorides coming in from the exterior. It's only the free chlorides, the chlorides in the pore solution, which can have an impact. So we are very interested in knowing how much of the chlorides will stay in solution, how much will be bound. And recently there was work giving thermodynamic constants for the binding of chloride in cementitious materials. It could also be that we were interested in the amount of alkalis or other things. This is an example on how this thermodynamic modeling can be used. And here you see the impact of the limestone filler on the faces in the system with the Portland cement. And it's assumed that we have full reaction. So what you see is that we, at a certain time, we have here, initially, if we don't have the limestone, we have some monosulfate. But when we add the limestone, we will have more ettringite and we will have hemicarbonate to develop, and later monocarbonate. And at a certain time, we don't use the calcite. You will also see that we can, given that we know the molecular volume of the faces, we actually can model the porosity. And here you have the data for the impact of limestone, here limestone percentage, as a function, the impact of limestone on the compressive strength. And you see that this increase in volume of the solids, it's actually reflected in the strength of the material. I propose a short break here. So